Okay, we've seen this transformation previously. Transformation takes a vector in R2 to another vector in R2. It can be defined, and you don't need the vector interpretation. This can be defined easily by this formula. T of xy equals 0.7x minus 3y, negative 2.1x plus 0.9y. First coordinate, second coordinate. So you're given the x and y coordinates of a vector. You get the x and y coordinates of another vector. Well, if we apply this transformation, let's say to these two vectors, which happen to be orthogonal, and they happen to be the simplest maybe vectors that we can use, a unit vector in the direction of x, a unit vector in the direction of y. Well, the unit vector in the direction of x has coordinates 1, 0, and I'm displaying these now as column vectors, which is what we were used to. This one as 0, 1, column vector again. Plugging in to the transformation, x equals 1, y equals 0, so here's where x is, here's where x is, so here's our x, the 1, and here's our x, okay, and y is 0, so here's y and here's y. Well, we do the arithmetic and we end up with this vector. Similarly, if we transform 0, 1, here's x, it's 0, here's x, it's 0, and y goes here and here, giving us negative 0.3 and 0.9. We get these coordinates. This transformation can also be represented by a matrix. Okay, if we put our 0.7 here and our negative 0.3 here, our negative 0.3, and our negative 2.1 here, and our 0.9 here, you can see that we get 0.7, that almost looks like a negative sign, 0.7 times 1, and a negative 0.3 times 0. Here we have negative 2.1 multiplied by 1, which is here, and 0.9 multiplied by 0 here. And similarly, then, if we multiply the same matrix by the vector 0, 1, we get the same result we do here, and it's easy to check that out. So we see that we get 0.7, negative 2.1, just as we did here, and we get negative 0.3, 0.9, just as we did here. Well, we can then say that, and I'll do this very lightly, that 0.7, negative 2.1, well, that would be a vector that comes out 0.7 units. Now this one comes out 1, so 0.7 would be about here. And then a negative 2.1, well, that's going to come down here, way down into here, so I'm not going to draw it here. I'm going to draw it on a new set of coordinate axes. And similarly, our negative 0.39, which we get when we transform the 0, 1, negative 0.3 would go over to about here, and 0.9 up to about here. So we're going to get a vector that goes down this way, and then a vector that comes back this way. Well, let's draw that. Now I want to set my axes so I've got plenty of room to go down here, because I don't need that much room for the vector that's going to go here. You can think about what that means. So I'm going to put my axes like here. Here's x, here's y. In this space, okay, now this version of R2 is going to be my space V, and this version of R2 is going to be my space W. And I'll label that here. So that my 1, 0 vector, which goes to 0.7, negative 2.1, Well, if 1 is this big, so 0.7 is maybe about here, and then negative 2.1 down here, no, to about here. Okay, so we draw the point 0.7, negative 2.1 over here. Our vector is going to go from the origin to that point. And similarly, our orange vector, our 0, 1 vector, will go to negative 0.3, 0.9. Well, let's see, negative 0.3 would be about here, and 0.9 would be about here. So we're going to have a vector that looks like this. Okay, so we have uh, 0.7, negative 2.1. That would be this form of the vector. And that we would represent by the column vector 0.7, negative 2.1. And over here, we would get the vector negative 0.3, 0.9, which we would represent by the column vector negative 0.3, 0.9. So we see that this vector kind of turns this way, goes up going in this direction. This vector kind of gets turned this way and ends up going in this direction. This vector gets longer, and this vector gets a little bit shorter. Okay, negative 0.3, 0.9 has a magnitude that would be the square root of 0.99, and this has a magnitude of 1. Now the square root of 0.99 is about 0.995, so this vector is just about as long as this vector. And actually, what I just said is ridiculous. It's not 0.99, okay? Because 0.9 squared is 0.81. It's 0.90, okay? And the square root of 0.90 is 0.95. Okay, so that has a magnitude of 0.95. This one had a magnitude of 1. So this vector gets very slightly shorter. This vector gets a whole lot longer. Okay, well, there's more that we could say about the geometric interpretation, but the one thing that I'll notice is this. This vector is parallel to this vector. Okay, so how do I see that this vector is parallel to this vector? Well, I'll write it this way. The slope of the line defined by this vector, the slope of the line that consists of all multiples of this vector, is negative 3. And you can check that, the y over the x, to change in y over the change in x here. That has a slope of negative 3. And negative 0.3, 0.9 has a slope negative 3. Very easy to check out. Okay, well, it gets even better. These two vectors are a basis of R2. Means any vector in R2 can be expressed as a linear combination of this one and this one. Well, any linear combination of these vectors is going to be along the same line here. So every linear combination of the two transformed vectors is along this line, which means that the image of every vector in R2 here has to lie along this line, meaning that we've collapsed R2 onto a straight line within R2. Now, I don't have a lot of room to write this, but I'll just comment that I'll say T transforms R2 into a straight line in R2. Meaning T takes a two-dimensional space and maps it into a one-dimensional subspace. So, 2 dimensions maps into a one-dimensional subspace of W. And we'll say the vector V, which is of 2 dimensions, maps to one-dimensional subspace of W. We collapse, in that sense, we collapse all of R2 onto this line. Okay, well, I could use some more words like projection and so forth, but I'll restrain myself for the moment. Okay, this is a big deal, and this sort of thing can happen as long as you have the right numbers here. And I'll also observe, I guess, that this matrix has rank 1 and nullity 1. Okay, so this matrix here has rank 1, nullity 1, meaning that, again, the set of vectors that you get when you use this matrix to transform a space is going to be one-dimensional. That's what the rank tells you. And the nullity is 1, meaning that there's a whole subspace over here that maps onto the 0 vector. Well, we'll follow up and we'll see how that works for this simple example.